Hello, Flutter Europe. How are you doing? So, yes, I've come here today to talk to you about the art of code. Now, the first computer that I ever had was one of these. This was an Amstrad 6128, and it was lame. It didn't have a joystick, it didn't have any good games or anything, but I was kind of obsessed with it. I was 7 years old when I first started playing with this. And the reason why I got obsessed with it was it had something on it called Logo. And Logo is what I wrote that little intro sequence there on an emulator in old 1980s Logo code, because Logo meant I could make the computer draw pictures. And then I switch it off and they disappear. But I knew it was there, and I loved that. I got this thrill out of making this computer do things on screen that maybe nobody had ever done before. And that kind of thrill of making the computer do something interesting, for me, and I hope for lots of you here, has never gone away. I still get that when I'm coding and, prototyping and building things. And we've had some amazing talks here over the last 2 days about computer programming for things that are important, things that are useful, solving real problems, design systems, domain-driven design, website engineering. But I'm not going to talk to you about anything useful. I'm going to talk to you about art. And there's a famous quote from Oscar Wilde: "All art is quite useless." But it's the keynote and there's no other talk, so you're going to have to sit here and learn about useless stuff. But maybe art isn't useless after all, There is another quote that I like. Douglas Adams said, "The function of art is to hold a mirror up to nature. Art can help us understand each other, our society, the world we live in. And if we want to hold a mirror up to nature, first of all, we have to invent the mirror. And that is where science and technology come in. Because for hundreds of years, we've used machines to see things in the world around us that nobody had seen before. We invented microscopes that have revealed this hidden world right underneath our noses, showed us things like this. This is the eyelid of a beetle under a scanning electron microscope. This is crystals growing in a dish of soy sauce. This is the spiral stems inside one fiber of a banana leaf. Beautiful, beautiful things that nobody had ever seen until we built the machines that allowed us to see them. And we've sent rockets and satellites and telescopes into space, and we've seen views of Earth no one ever saw before. We've looked back from beyond Saturn. We've seen our little pale blue dot there in the corner. This is a thing called the Pillars of Creation. It's 6,000 light years away, and we've built machines that can take photographs of it and show us what this looks like. And we've also started to discover another hidden world, a world of mathematics and information that we can explore using software and modern computers. A guy called Martin Gardner wrote a monthly column for Scientific American magazine where he talked about mathematics and puzzles and logic. And in this edition, October 1970, he described something called John Conway's Game of Life. Now, the Game of Life it doesn't look like a very exciting game. It's a game that's played on an infinite grid with no players, and it has 4 rules. The rules of life. Each of these little grid cells can be living or dead. And the rules are, if a cell has 0 or 1 neighbors, it'll die of loneliness. If a cell has 2 or 3 neighbors, it will survive. If a cell has 4 neighbors, it'll die of overcrowding. And this is the spooky part. If a cell has exactly 3 neighbors, it'll come back to life. That's it. Those 4 rules are the whole of Conway's Game of Life. And when this was first published in 1970, people used to figure out what these rules meant using graph paper. And they would draw graphs on bits of squared paper and try and figure it out. And this can give you sort of some insight and understanding into how these systems behave, but it doesn't really show you what's going on with them. If we take these 5 basic shapes, the 5 tetrominoes, sketched out on paper here, it's like looking at butterflies in a museum, pinned up in a glass case. You can see what they look like, but you don't really understand how they behave. In the 1970s, people started using computers to simulate the game of life, and they found some really cool stuff. These are the 5 tetrominoes, and this is how they evolve. 4 of them settle down really quickly, but one of them goes into this infinitely repeating pattern of these little crisscross shapes that we call traffic lights. One of the earliest questions with the game of life is the grid bounded, or is it infinite? In about 1973, a team working with a guy called Bill Gosper discovered this shape, which they called the glider. And the glider just glides across the infinite grid, repeating itself every 5 generations. Now, one of the other questions they had is the game of life bounded, or will you get shapes that grow infinitely? And then they discovered all of these. These are all glider configurations coming from those same 4 simple rules. These are called spaceships, and there are hundreds of these, as weird and wonderful as anything you'll see on TV or Star Trek or Babylon 5. But then they started discovering some really cool stuff. This is a configuration. You've seen the glider already, but Bill Gosper's team discovered something called the glider gun. This is a stable configuration, and every 27 generations, it creates another glider and sends them streaming across this grid. We now have a signal generator in the game of life based on those 4 rules. They discovered another pattern. This thing is called the eater. It consumes gliders. And now we have a way to create a signal and a way to destroy a signal. We have 1 and 0. We have true and false, and we can build logic gates. This is an AND gate implemented in Conway's game of life. So here are our inputs, A and B, and this is our output, A and B. Now, if we take this blocker out of the way so that input A becomes true, and we run our circuit, nothing. The output is still false. If we switch it around so that B becomes true and we run our circuit again, nothing. The output is still false. If we enable both of those inputs, A and B, and we run the circuit, we get true on the output. We get a signal coming through. Now, this is incredibly exciting because if we can build logic gates, we can build circuits. And if we can build circuits, we can build computers. And if we can build computers, we can run programs. Like this one. It's a program called Conway's Game of Life that you might have heard about recently. Four simple rules. 4 rules, 1 infinite grid. Now, Conway's Game of Life is one of a whole category of systems that exhibit really complex behavior starting from very, very simple sets of mathematical rules. The name they have for this kind of really complex output from simple inputs is sometimes called the butterfly effect. And one of the great examples of these kinds of systems is an area of mathematics called fractal geometry. The pioneer in this, there was work done in the early 19th century by 2 mathematicians in France, Pierre Fatou and Gaston Julia. But because they were doing it on graph paper, they never really understood what they had discovered. We didn't know that until this guy came along, Benoit Mandelbrot. He's a Polish mathematician. He lived in Paris. He did most of his work in the US. And he was obsessed with using mathematics to try and understand the world around him. He had this very famous quote: "Clouds are not spheres, mountains are not cones, coastlines are not circles. Bark is not smooth, nor does lightning travel in a straight line." And using his mathematical insight, he had a brilliant job. He taught mathematics at Harvard, and when he got bored, he'd go and hang out at IBM and play on the computers, and then he'd take those ideas back to Harvard and he'd teach mathematics. And using those early IBM computers, he became the first person ever to see the shape that now bears his name. This. Now, his name was Mandelbrot, but everyone calls this the Mandelbrot set. So, the Mandelbrot set. Now, this was the first visualization of this shape. This shape comes from one single equation, just crunched again and again and again. These days, we have high-definition color displays. When we draw the Mandelbrot set, it looks more like this. You've probably seen this shape. But the astonishing thing about this is from that one equation, there is an infinity of complexity. We're going to start with this Mandelbrot set, and we are going to go on a little journey, and we are going to zoom in, and we are going to say that now we are at factor 1 magnification, and we're going to keep zooming in, and we're going to keep zooming in. By the time we get to round about here, the original shape is bigger than the building that we're in. By the time we get to about here, this is 2 to the 20 magnification, the original shape is now bigger than Warsaw. And more detail, and more detail, and we keep zooming in. The original shape is now about the size of Poland, and we're not going to run out of detail, because we never are. Because there is an infinity of beauty and complexity that we never saw until we invented computers and the arithmetic and the tools that were necessary to allow us to do this. And this isn't something anybody created. This is something that was discovered. Like an Easter egg hidden in reality. Well done, humankind. You've invented mathematics and computers. We've left this here to convince you you're on the right track. And I think that's cool. I think that is amazing and beautiful. But we've reached a point now where computers are so powerful that there's almost no limit to what we can see on a screen. In 1982, Disney made Tron, which was the first mainly computer-generated motion picture. Tron was disqualified from the Oscars because they said using a computer to make a film was cheating, and you weren't allowed to do that. We've had the first completely computer-animated film, Luxo Jr. in the 1980s. We've had computer-generated dinosaurs interacting with real human actors. A couple of years ago, we had this guy on our screens. And there's this big argument where the actor Peter Cushing's family are going, you can't do that. And Lucasfilm are going, but that's not Peter Cushing. That's a character called Grand Moff Tarkin from the Star Wars films. So we can literally use computers to bring kind of dead people back to life and put them up on screens. We can even turn to our computers and go, hey, what would it be like if they remade Friends and they got Nicolas Cage to play all the actors? Now, the reason we can do things like this is we've trained computers to work in a very similar way to our own brains. You ever lie on your back in a field on a cloudy day and you see clouds kind of drift overhead and they look like shapes? That one's a rabbit and that one looks like a cat and, that one's an airplane. No, that is an airplane, hang on. And, your brain is coming up with these patterns. It's recognizing things. And within the last 10 years, we've done lots of very successful research on training neural networks to work in a similar way. Now, we don't exactly understand how they work, but we've worked out how to build them and train them. You take these layers of recognition matrices, something called a convolutional neural network, and you train them on a load of inputs. And you let them figure out for themselves how to tell the difference between, say, a cat and a dog. Now, sometimes this is a lot harder than it looks. One of the big challenges in machine learning and computer vision is how to tell the difference between a puppy and a muffin, which doesn't sound like a big deal until you look at some of the input data. Now, this is all very cool and very interesting, but what's really cool is somebody took this neural network that is used to recognize dogs in photographs, and they basically flipped it around backwards, and instead of being a dog detector, they turned it into a dog amplifier. And then they fed in photographs which have nothing to do with dogs and said, find the dogs. And the computer goes, no dogs. And you say, no, find the dogs, look harder. And when you find them, enhance them. And the computer goes, this is a horrible idea. And we say, no, turn up the power, more dogs. And what this is doing, this is a technique called deep dreaming. It came out of the Deep Dream project at Google in 2015. And what it's doing is it's exploiting the same kind of circuits we have in our brain. That, like when you're walking through a forest late at night and all the trees look like murderers until you look and know that's a tree, murderer, tree. It's the same kind of short-circuiting pattern recognition. It's finding things which might slightly have some kind of dog-like behavior, and then it's just exacerbating and exaggerating those elements of it. Now, we have, and I didn't know this until I got here, we actually have somebody right here in the organizing committee of this conference who's been doing some really cool stuff using Flutter and Dart to create procedural art. Check this out.
When I start a new artwork, it's just an inspiration. You just have a feeling. So between the first idea and the end result, there's just the same feeling. It's not about the visual. I'm not interested in what you see. I'm interested in what you feel. I'm Robert. My everyday job, I'm a Flutter dev and project manager. And I'm also a Flutter artist. Previously, I was kinda locked by the tool. I can do a lot of stuff, but only what the tool permits me. When I found Flutter, it opened a door inside me. Now I can really push further. Generative art is a lot of research, like a lot. It's a lot of failure. It's a lot of failure finding the color, finding the form, understanding the good behavior of light. What's really good with Flutter is the speed of the feedback. It's nearly instant. Currently, artists do not understand the full potential of the tool. When you start Flutter, you start with material design, or you start with the iOS component, and you think this is Flutter, but this is just the tip of the iceberg. Or if you want to push, then you start to enter the Flutter engine. And the Flutter engine is like the jewels of the crown. Each time I start to code, I just feel joy. So some people are painting, some people are cooking. I just do Flutter. I'm fluttering.
Now, I was talking with Robert earlier today about this, and he showed me some of the things that he's shared on Twitter. And there's one I wanted to put in this talk just because I think it's absolutely beautiful. And it's this. And what's happening here, this started as a photograph taken in Tokyo at night that was then run through some machine learning models to extract depth information. But then all of the visualization that's happening here has been built using Flutter and sort of artistic input in terms of defining colors and gradients and things to recreate this image by drawing up layers based on the depth of the objects in the picture. And I think it's beautiful. It's kind of hypnotic. You watch it looping and looping, and every time you start noticing little things that you've not seen before. And as Robert says in the video there, one of the things about art is the immediacy of feedback. You know, if you're trying to capture a feeling in your head when you're working in paint or clay or software, you need something that responds instantly. Otherwise, you lose your inspiration, you lose your thread. And I'm really interested in seeing what Flutter as a platform is going to be able to offer, like generations of computer and generative artists and stuff. So we've talked about using computers to create art and render things and draw things. But now I want to talk about what happens when the software itself is an art form. There is this debate that has been going for many, many years. Is programming engineering, or is it creative, or is it art, or is it technical discipline, or, you know, are we just glorified typists? There's this very famous Donald Knuth's book, The Art of Computer Programming, which is like the Bible of data structures and algorithms and these kinds of things. But I'm sure all of you have reviewed some code, or maybe written some code of your own that you came back to later, and you open that code up and you're like, I don't know what this is. It's not art. It's not engineering. I wouldn't call it science. It's creative, I'll give it that much. And when you're managing a team or you're pairing on stuff, that can be a challenge. And how do you deal with it? How do you do code reviews effectively? But fortunately, there is a safe space for this kind of code. And it is the International Obfuscated C Code Contest. The goals of the contest are to write the most obscure C program, to show the importance of programming style in an ironic way, to stress C compilers with unusual code, to illustrate the subtleties of the language and provide a safe forum for poor C code. Now, I want to have a look at a recent submission. Any C programmers in the room? Anyone want to read this code and tell me what it does? What the hell? Let's run it and see what happens. So I'm just going to make that, and I'm going to run it, and there it is. That's Flappy Bird running in a Unix terminal in text mode in just under 1,024 bytes of source code. And it is just as difficult as every other Flappy Bird ever made. And, there are whole generations and wonderful creations of these tiny, minimalist, obfuscated programs. This is 1 kilobyte of JavaScript. That's it. That is the entire program. If you paste this into a web browser and refresh it, it plays chess. It's called Nano Chess, written by a guy called Oscar Toledo G. And I don't mean it draws a chessboard, I mean it plays a game of chess, and it actually beats me. It is a better chess player than me in 1 kilobyte of JavaScript, which I just think is fantastic. Now, there's been this sort of race to see how minimal we can get these kinds of programs. And in 1994, a guy called Simon Rosinkiewicz submitted this to the International Obfuscated C Contest. This is an empty file. And he submitted it with a note saying, if you compile this using this compiler, that compiler, if you gave it an empty file, it would produce a program that created empty output. And he said, this program produces its own source code when it is run through certain compilers. And the C code competition said, that's very impressive, well done. They gave him a special prize, and then they changed the rules and said, your program must have at least 1 byte of input. Otherwise, it's just the same as this program. But this gets us onto the idea of something called quines. Now, a quine is a program that prints its own source. And you can't just read it from disk and print it. You have to actually generate the program source from the program, which kind of sounds easy until you try and do it. So C# is my preferred language at the moment. So I tried to write a quine in C#. So I got this, class program with a static void main. I'm like, all right, well, I need to output program and the closing brace, and I need to output the static void main. And then I'm like, well, hang on, because now I need to console write line the console write line and very, very quickly you get into this kind of infinite loop. So to build quines, you need to exploit loopholes in the design of your programming languages. C# has something called string templating, which is supposed to be used for, string formatting and outputs and things. But we can create a string like this, which has these 010 placeholders in it, and then we can feed that string back into itself, and we get the source code to our program at when we run it. Now, building quines is a lovely way of understanding the capabilities of different programming languages. JavaScript makes this really easy because you can just take any function and put toString on it, and it outputs itself. And in ECMAScript 6, this is a quine. And I didn't believe that, so I ran it. And that's what it does. This program produces its own source code. Now, there's a guy called Leon Bambrick, and a little while ago, he posted something I just thought was fantastic. He built a quine in HTML. This is a web page. This is the HTML source code, and we view it in a browser, and it looks like this. And now I'm going to exploit the loopholes in the browsers and CSS to make this web page print its own source code. So first thing we're going to do, we're going to put in a style sheet rule that says star, so everything, display it as a block. And suddenly, we've got our title, and we've got our head, and we've got our body elements. Now we're going to use some CSS rules to say, add this content before and after the HTML tag, Opens with HTML. It's closing as well, but it doesn't know where to draw it on the viewport. We'll fix that in a minute. So we're now going to plug in before and after. Now you'll notice here, where we say style after, we need to escape the slash. That's to stop the parsers fighting over who gets to own this line of code. Feed that back through. Now we have our style sheet being rendered in the page source code. We plug in before and after for all the different tags we're using. Now we need to add a rule that says if there's a link on this page, we want to show the href for that link by adding some content to it. That plugs that in, that works. And finally, I'm just going to plug in a little rule here, puts a margin on the HTML and changes the height. And now we have a web page that displays its own source code, which is completely useless, but it's kind of fun, right? Now, who wants to tell me, take a look at this code, and tell me what language it's written in. Did someone say C? C, all right. So I'm going to apply now some syntax highlighting, but this is what the C preprocessor will do to this. So that looks like valid C, right? We've taken out the comments and highlighted the strings. Yeah, looks pretty good. Now I'm going to apply some Ruby syntax highlighting. Now this is interesting. And I'm going to highlight the string literals. And that looks like valid Ruby. So what is it? Is it C or is it Ruby? Well, there's only one way to find out, right? Let's run it. So here is the source code, polyquine.c. There it is. I'm going to run that through GCC. And then I'm going to see what the output of that is. We get one warning, but hey, nobody said this was a good idea, right? And that program prints its own source code. But now I'm going to run the same program through the Ruby interpreter. Because why not? And there it is. It prints its own source code. And now I'm going to run the same program through the Python interpreter. And there it is. And now, just because, hey, we got this far, let's run it in Perl and see what we get. It prints its own source code. And if you can find a C++ compiler that doesn't mind if main doesn't return an integer, it works in C++ as well. This is a thing called a polyquine. It's a program that is syntactically valid in this case, 5 different languages, and it prints its own source code in all of them. But we're just getting warmed up. What language do you think this chunk of code is written in? Well, let's figure it out. So we've got system.console here, which is kind of like probably a .NET C# kind of a thing. And we've got an XML namespace here, which is XSLT, I presume. And down here we've got for each and console.log, which looks kind of like JavaScript, right? And we've got an Ada text. Any Ada programmers in the Flutter community? We have one. Is this look like good Ada code to you? And we've got begin here in all block capitals, so that's a business language. It's either SQL or COBOL. And then up here, we've got Act 1, Scene 1, Enter Ajax, which doesn't even look like programming at all. This thing is brilliant. This is written by a developer called Yosuke Endo, who is one of the Ruby language core contributors. It is a Ruby program that creates a Rust program, that creates a Scala program, that creates a Scheme program. It goes through 128 languages, and you end up with a Rex program, and when you run that, you get your Ruby program back again. This is the Ouroboros quine, the snake eating its own tail. And the most beautiful thing about this is that the entire source code to it looks like this. 128 languages, and if we zoom in on the end, you'll see one of the cool little details about this is all of this space has been reserved so that they can fix bugs in the program without messing up the shape of the source code. And that's not even the coolest thing about it, because all 128 of those languages are available using apt-get on Ubuntu Linux. And so there is a continuous deployment pipeline which runs all 128 languages and verifies that you get your output back at the end of the route. But let's backtrack a second. What was Act 1, Scene 1, Enter Ajax? Well, it turns out one of the programming languages here is a thing called Shakespeare. And Shakespeare is an esoteric language, an esolang, which is designed to let you write computer programs that read like Shakespeare plays. So this is Hello World in Shakespeare. All of your variables are characters who must be introduced. So we have Romeo and we have Hamlet. Instead of blocks and methods, we have Act 1, Scene 1. Enter Hamlet and Romeo, that's variable scoping. Now, you increment variables in Shakespeare by saying positive and complimentary things, and you decrement variables by insulting them. So Hamlet says, "You lying, stupid, fatherless, big, smelly, half-witted coward. You are as stupid as the difference between a handsome, rich, brave hero and thyself. Speak your mind." That prints H. It calculates the ASCII character code for a capital H, and then speak your mind is output. And then the next block there prints E. So Hello World is about 2 pages long in Shakespeare, which is kind of fine, because, you know, Shakespeare wrote some quite lengthy plays. Here is Hello World in another one of my favorite languages. Anyone know what this one is? Whitespace. It is. This is the Whitespace programming language. I'm going to apply some syntax highlighting here. Whitespace ignores everything except spaces and tabs. Whitespace is brilliant for hiding programs inside other programs, because most programs ignore whitespace, but Whitespace loves it. It's the only thing that means anything. Everything else is a comment and gets ignored. Now, there is another language which I particularly like. It's a language called Chef. And the idea with Chef is to write computer programs that look like recipes. This is the kind of canonical Hello World in Chef. Now, this is interesting, but if you look at that recipe there, 72 grams of beans, 101 eggs, 108 grams of lard, 33 potatoes, this is a very interesting salad, you know. It's a program, and it looks like a recipe, but it's not a recipe anybody would ever actually make. So a couple of years ago, a guy called Mike Worth created this. This is the Hello World chocolate cake. Not only is it a valid Hello World program in Chef, but it also makes a chocolate cake with chocolate sauce. So you choose your hardware. If you run it on a computer, Hello World. If you run it on your kitchen, you get this cake with chocolate sauce. That apparently it needed the sauce because the cake was a little dry, but it's a recipe. It's a valid recipe. And if you didn't know it was a Chef program, you might be completely unaware there was any software here at all. Let's have a look at how to square a number in the programming language called Pete, which is named after Pete Mondrian. This is the source code for squaring a number, because Pete is a graphical programming language. This is the instruction set, and these are the color shades. And the way a Pete program works, we have an instruction pointer that starts in the top left corner. Every time it crosses a color boundary, that's an instruction. So we've gone from light blue to dark green. That's the instruction code for input. When we get to black, we change direction. When we cross from green to red, take whatever's on the top of the stack and duplicate it. Red into yellow, multiply the top 2 values on the stack, put the result on the stack. Yellow into red, output that number. Anything that crosses white is a no operation. When we get to the edge of the grid, we turn right, we turn into blue, and we follow that blue shape until we end up with black on all sides, which means your program has finished and you can halt. Now this is Hello World in Pete. And you could print this out and frame it and hang it on the wall, and nobody would ever know they were looking at a computer program. They just think you like kind of slightly funky geometric art, right? Now, I love all these kinds of ideas. I love, you know, esoteric languages and the creativity that goes into designing them and creating them and stuff. And we have this idea in software about being able to reproduce things reliably, right? We've all worked with continuous unit testing, integration testing, automated deployments. We don't ever want any variations. We want to take all the risk out of it. Now, at conferences like this, there's always a couple of people who do live demos. Now, I quite like live demos because they have this kind of element of risk. What if it doesn't work in it? And it kind of turns coding into something akin to performance, right? Now, I wouldn't ever recommend anyone does live performance coding on mission-critical systems. I've seen people do it, and once I saw someone get it very badly wrong. And we have this term in software for fragile servers or fragile processes, right? We call them snowflakes. because they're unique and they're special. But the thing about a snowflake, if you grab a snowflake out of a blizzard and you watch it melt on your hand, you've just been part of an experience that nobody else will ever be involved in. And you cannot share it, you cannot replicate it. You've just been a part of something unique, a unique performance that will never take place ever again. And I want to explore this idea of how we can use software as part of performance. Now, this guy in the picture, sat up here with the London Philharmonic Orchestra, is a guy called Sam Aaron. And Sam created a programming language called Sonic Pi. Sonic Pi was designed to help kids get into computer programming. And Sonic Pi is a live, real-time programming language for performing music using code. And I'm just going to show you a little demo now of what Sonic Pi actually does. So you open your Sonic Pi interpreter and you say, I want to play this note, and it plays it. Now, Sonic Pi is the only language where it will run all of your code simultaneously at the same time. Imagine if JavaScript did that, unless you tell it not to. So we're going to play these 3 notes, and we're going to put a delay in there. And now we can go in and say, well, actually, we don't want to map this out. Let's put a loop in here. Let's build ourselves like a little looping bass line here. So it's looping. Now, this is not musically terribly interesting, right? So I'm going to crank up the tempo a little bit. I'm going to say use beats per minute, 244, get something with a bit of energy behind it. And then I'm going to take this sine wave, and I'm going to say, no, I want to use one of the built-in synthesizers, a thing called Texors, because I think it sounds cool. And we're only just getting warmed up. Because the really, really brilliant thing about Sonic Pi is it has a feature called live loops. A live loop lets you run and modify code while it's executing, so you never need to restart your program. So I'm going to kick off this live loop here. And then I'm going to drop another loop in on top of it, which is synchronized with that main loop, that is going to give us some symbols. And then I'm going to grab this, which I have prepared in another buffer, and I'm going to drop this loop in on top of the program at the same time. Now I'm going to put a counter into my loop up here, and I'm going to say, well, okay, if the number is divisible by 3, I want you to play this note, otherwise play that one. And now I'm going to put another rule in there which says, okay, if the number is divisible by 5, play this note, and if it's 3, play that note. And can anyone guess what the last case I'm about to plug in here is? Divisible by 15, 3 and 5? Play that note. Does that algorithm look familiar to anybody? FizzBuzz. FizzBuzz implemented as a baseline, as a riff in real time, using Sonic Pi, which I think Sonic Pi is brilliant. I've seen people do like full live band performances with one of them typing loops and samples and things on laptops. It's absolutely fantastic performance tool, and it's a different way of thinking about code as well. It's doing something with software which isn't quite like running programs or writing code that someone can come back and run later. Now, I have one more part of this talk. I've talked about all kinds of amazing and wonderful things that have been created and shared by other people, other developers around the world who have too much time on their hands, probably. And I want to tell you about something I did. Now, you're probably familiar with the trope of the rock star developer, right? Because there's these advertisements all over the world about people looking for rockstar developers. Rockstar front-end, we need a front-end rockstar, back-end rockstar, database rockstar, this rockstar, that rockstar. And a couple of years ago, somebody put a thing on Twitter that just said, to really confuse recruiters, someone should make a programming language called Rockstar. And I had this experience, this moment of blinding divine revelation. I thought, this is why I'm here. This is what I need to do with my life. Because when I wasn't goofing around on Amstrads and learning programming and all this kind of stuff, I wasted my youth under the influence of these fine people, the hair metal rockers of the 1980s. And I thought, that's what we need. We need a programming language for creating programs that are also rock songs. Bad rock songs. Bad 1980s power ballad rock songs. Now, I invented the Rockstar programming language in a bar. This is important, and it'll become apparent why it's important later. But I sat down and I started playing around with ideas from languages like Perl and Ruby and VBScript. First of all, Hello World. I thought, well, let's have lots of different ways of doing things. So you want to do Hello World in Rockstar? Say Hello World. Or scream Hello World. Or whisper. Or shout. Any of these is fine. Depends what kind of song it is you're trying to write that day. Now, to be able to program computers, we need variables and we need assignment. And I'm sure you've all seen languages that look like this. X equals 5 and my string equals this and var and so on. Now, I decided Rockstar was going to be dynamically typed and it wouldn't need semicolons because, hey, we can do that. Ruby does that. JavaScript sometimes does that, maybe. We don't need to declare types. Variables are declared by using them. I didn't want equals because equals it's not something you can sing. So is was the assignment operator. Now, have you ever had an argument longer than, say, 3 hours about whether to use underscores or Pascal case or camel case or, yeah, I have. And I saw Douglas Crockford give a talk last year where he made this really interesting point. He said, we have all these discussions about Pascal case and camel case. What we want are variable names with spaces in them. And I thought, all right, I'm inventing a language in a bar as a joke. We can have spaces, that's fine. 3 kinds of variables in Rockstar. There's simple variables, which are just like they are in most languages. Common variables have to start with my, an, your, a, the, so you can have these little 2-word variable names. And then proper variables need capitals. Dr. Feelgood, Black Betty, Billie Jean, all these great rock and roll names. Now, to be able to write a program like FizzBuzz, you need to initialize numbers with values, 3, 5, 100, and this is not terribly rock and roll, right? I wanted to come up with a better way of initializing them. So I had the idea, what if we take the is keyword and we say, well, let's count the lengths of the words on the rest of the line, modulo 10, and treat each one of those word lengths as a digit to initialize decimal numbers. Yeah? Makes sense. And then I thought, how does this work with decimals? Now, in C#, pi equals 3.14 blah, 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 m, semicolon. In JavaScript, var pi equals, and if you're lucky, you'll get almost that number back when you're finished with it. To initialize pi in Rockstar, my heart was ice. 3, a life unfulfilled, waking everybody up, taking booze and pills. We're just getting warmed up. Arithmetic. I didn't want operator symbols. All of this needs to be stuff you can sing. So addition, well, in English we say it's the price with the tax. It's the total without the tax. It's the quantity of the product. It's the distance over the time. But this also means you can write arithmetic like a girl with a dream, a man without a face, the wings of the night, a whisper over the water. For comparison operators, your love is a lie, true or false. Well, is it? The whiskey ain't the answer. My heart is stronger than steel, my soul's weaker than water. My will is as strong as a lion, your lies are as low as a snake. Needed a way to implement functions without using brackets and block syntax and all this kind of stuff, so I thought, all right, modulus takes a number and a divisor. Takes is the function declaration syntax there. While a number is as high as a divisor, put a number without a divisor into a number, assignment, give back a number. There's a blank line there, that's what terminates the while loop, and there's another one at the end that terminates the function. And this is arithmetic modulus in Rockstar. But this is kind of not terribly rock and roll. So what if midnight takes your heart and your soul, and while your heart is as high as your soul, put your heart without your soul into your heart, and give back your heart. At this point, I've had several beers, and I think this is done. I stick a draft up on GitHub, and I put a thing on Twitter, and I said, hey, there's this new language, go and have a look. And it goes crazy. Within 24 hours, it had 2,000 stars on GitHub for a repo containing one joke specification. It made the front page of Hacker News. It made the front page of Cory Doctorow's Boing Boing did a write-up about it. It made the front page of Reddit. I just kept getting all of these little funny comments, why doesn't it go up to 11? Someone saying the docs are hilarious. I'm sold, shut up and take my money. Then the really weird thing happened. I got an email from Classic Rock magazine, which is a real music magazine that normally interviews Red Hot Chili Peppers and people, saying, what's this Rockstar thing we're hearing about? And they did a whole feature on it. And I got in Classic Rock magazine for a joke programming language. And that's not even the weirdest thing that happened. People started filing issues on the GitHub repository. And I went back to these people, and people were filing issues like, there's undefined behavior in your specification. I was like, so? Why would anybody care? And they say, because my compiler doesn't work. And I said, what? And I said, I built a Rockstar compiler in Scala at the weekend, and it's got edge cases where I don't know what the correct behavior is. And within a week, there was a Scala implementation. Someone had built one in Rust. Someone had built a transpiler from Rockstar to Python. Just this absolute flood of interest and enthusiasm. And I kept thinking, it's going to die down anytime now. This has got to be the end of it. And it didn't. This thing just kept going over and over. And I reached a point where I thought, I like people saying, oh, Dylan Beattie, the creator of Rockstar, but I didn't feel right taking the credit for something that I did in one evening in a bar. I thought I need to put the hours in and actually come up with something. So I built my own Rockstar interpreter. It is hard implementing a spec that you made up while you were in a bar, but about 95% of it actually proved to be implementable. And I did it in JavaScript, and I did it in JavaScript for a very good reason. I wanted to put an interpreter on the web that anybody can go to in a browser, and they can just open it up, and they can type some code and become a Rockstar developer right there and then. So I built codewithrockstar.com with a JavaScript interpreter behind it. Now, that shiny 1980s rock and roll logo up in the top corner there, I just need to give some credit to where that came from, because I wanted to pick up on something really excessive, 80s rock and roll, big hair and fast cars and all that kind of stuff. And I was looking around for inspiration, and somebody said, have you thought about Microsoft consumer products? And I thought, that's exactly what I want. That typography is perfect. And it turns out Microsoft aren't using that logo anymore. So I picked it up. Thank you, Microsoft, for letting me recycle that. Now, I do have some certificates for the Certified Rockstar Developer Program here with me to give away at the end of the talk. So go to codewithrockstar.com, try something out, show me, and I'll give you your certification. And I'd like to close the talk with one little kind of creative software coding experiment, if that's all right with you. Because the whole idea, the premise behind Rockstar was to write programs that could also be songs. And of course, that only works if you can play the songs for people and they sound okay. And when I say okay, we're talking like, Bad Meatloaf from the 1980s kind of okay. So I would like to perform for you now Fizzbuzz in Rockstar, live at Flutter Europe. Is that all right with you? into your heart. Give back your heart. Now you remember the fizz buzz riff? Flutter Europe. That was awesome. Thank you. Now, I think, a little time for questions. Do we have a little time? I do have one important question for you, which is, where's a good place to go drinking in Warsaw on a Friday night? So if anyone's got a good answer to that, come and see me afterwards. It's my first time in the city. It's been awesome so far, and I have the night off. Does anyone have any questions or anything about any of that? Or have we achieved complete enlightenment? We have one way up at the back there.
Hi.
Hi.
Is your language supporting metal umlauts?
Yes.
That's great.
I can actually show you if I can get it up. I'm not on the Wi-Fi, but it's open source. If you go and have a look at the parser, it uses a thing called a parsing expression grammar, and there is this massive chunk of text in there which defines all the valid identifiers, and yes, umlauts are valid in all variable names. At one point I thought of making them mandatory, but I thought that would make it difficult to type on a phone if people don't know about it. But yes, it supports full metal umlauts. There's another question over that side.
What about handling exceptions?
So the draft syntax, which hasn't been implemented yet, the problem with classic rock music is there are no mistakes in classic rock music. So we had to take some inspiration. I had an idea about why don't we use punk music instead? And so what we can do is the way that in IEEE you can have a division that returns nan, and in some languages you have error codes. What I thought is we have a special keyword in the language called bollocks. And if something fails, it returns bollocks. And if you want to, you put never mind the bollocks at the top of your program, and that means you use like VB script on error resume next, exception handling. And so that's the draft syntax for exception handling. But I don't think that's going to make it in, because it's a little bit too punk. Any other questions? What? The album? Soon. So what I want to do with this, I want to put a couple more things in the language because it's not finished yet. But then I want to do a Rockstar programming competition. And the prize is the 10 best programs. I will go into a studio with my band and we will record them as actual songs and release that as an album of procedurally generated, compilable, bad rock songs. But that might take a little while. Give me another year. Any other questions? The closest I've got is Rock You Like a Hurricane by Scorpions. It doesn't do anything, but it's about 80% syntactically valid. And I think with a couple of tweaks to the language spec, I can get the whole thing to compile. But all it does is just declare a bunch of variables. But I have there's an array syntax, instead of push and pop, it uses rock and roll. So rock you like a hurricane takes a hurricane, counts 1, and then hurricane is 9, so that's 19, and it increments the array u by pushing that value on the front. So yeah, it's almost there. Scorpions is almost accidentally programming metal.
Yeah. Sorry, I have really one question now. Now tell me that the song you played last night at the party, they compile?
No.
They actually... it will blow my mind.
Some of them don't even rhyme.
Have you considered throwing syntax error when lines don't rhyme?
Difficult. Not impossible. But don't give me any more ideas. Any other questions? Brilliant. We've achieved complete enlightenment. Thank you, everybody. That's been awesome.